So we will be actually. Can you guys hear me by any chance? Because last time I did the live, I knew people were not able to see. I mean, people were not able to hear. I just want to see if people can hear me. No, not here. You can hear me, right? You can hear me, right? And why is the resolution so less? Let me just see why is the resolution so less. Huh? Streaming? Yeah, I don't think I can change it, right? Okay, no worries, no worries. Let's not focus on that. Yeah, let's not focus on that. I mean, it's night anyways. All right, so we will be doing the the aerospace. So we're gonna finish off section 1.4. So we finished section 1.3. Actually, we need to finish 1.3.2 and 1.3.3. I'll try my best to uh, procrastinate as less as possible because I have this bad habit that I procrastinate a lot, which is not good. It's not good. All right. Um, First of all, let's see like so based on you know the context and the text, like based on the transcript and the text and whatever, transcript and text and whatever, like text actually shown, what chapters are covered here. We'll go 2 hours, so no break for 2 hours, no procrastination for 2 hours. We'll try our best to finish off as much as possible within 2 hours. If you have any notes, you can finish your notes. If you have any assignments, if you have any homeworks, if you have any studies to go through, you can uh, f- try not to procrastinate as much as possible. Just know that you're good enough. Just know that whatever you do within these 2 hours, it'll be great. It'll absolutely be great. Even a little bit of session, even if you want to study for 1 hour, that's completely fine. You're free to leave the live session if you don't want to study at all. But try your best to do 1 hour, then 1 hour. All right. I'll try my best to keep the procrastination level as low as possible. So I believe everyone can see me. Kick, you can see me. X, you can see me. So glad to know that everyone can see me. I know the views here is zero, but even then, people can see me. People can. So that is great. But let's proceed. So based on the transcript and text shown, what chapters are covered here? Only share the only share the section. What section? What sections are covered here? All right. So I see that there are oh shit, there are 40 subchapters. Is it possible like if we can combine uh 4 chapters, like 4 sections into one, if that's possible? Can we combine 4 sections into one? Meaning we can have 10 sections where one section explains one like master section explains 4 subsections, 4 sections. We'll do that then. Cool. So we're gonna have 10 master sections. All right. Um, I do have the abstract. Okay. So based on the abstract shown, please create a latex code. Speaking of latex, please create a latex code in correlation to this abstract and label this explanation as chapter section actually subchapter 1.3.2, and it is TL versus delta L trim. TL trim versus uh, delta E trim, and have 10 sections explained. Have 10 sections explained, thorough, easy. One thing is that I got my Wi-Fi, which is excellent. Excellent. So I got my Wi-Fi, so we can stream as much as possible. We can learn as much as possible. Like there shouldn't be any worries now. Hopefully. Or that begin document, whatever. Here, put a star here. What's that do? Right? Good. So easy. Let's learn. So during the rocket and missile ascent, disturbances such as wind gusts, thrust mismatch, atmospheric density variation, aerodynamic uncertainty continuously disturb the trajectory. Adaptive guidance systems therefore require continuous trim correction and longitudinal stabilization. One of the most important relationships in longitudinal flight dynamics is delta E trim versus the coefficient of lift trim. So pretty much they explained everything. Any rocket ascent or missile ascent, any aeros vehicle ascent. So any aero vehicle ascent, let's say if for example, the rocket launches or the missile launches, what happens is we are going to have wind gusts, we are going to have the thrust mismatch, we are going to have atmospheric density variation, we are going to have aerodynamic uncertainty. Anything can happen. Anything that correlates to the wind, anything that correlates to the atmosphere, anything that correlates air, there are changes. And they change continuously. And these are the core that continuously disturb the trajectory. The adaptive guidance system therefore requires continuous trim correction and longitudinal stabilization. One of the most important relationships in longitudinal flight dynamics is delta E trim versus the coefficient of lift trim. Try it now. So, step 1. What are the core criteria that play a role in aviation that disturb trajectory? So, what are the core disturbances during the airspace trajectory? So obviously you can have wind gusts, you can have thrust mismatch, atmospheric density, aerodynamic uncertainty. So wind gust, thrust mismatch, aerodynamic uncertainty, and atmospheric density uncertainty. What do I mean by atmospheric density is because initially you're gonna have high atmospheric density, which means the gravity pulls you down, right? And so that is why you're gonna need more thrust at the beginning of the launch, because you want to make sure that the missile goes up. Because at the ground the air density is the highest, it's peak highest. But as you leave the Earth's stratosphere, you're gonna have less air density. So that's why you keep on floating around, right? To a point where when you reach that stratosphere limit and you go outside the stratosphere limit, you're in a vacuum now. So there is no density, it's zero. there it is fully zero. And because the air density is zero, you will not be able to breathe also. This is why you have this is why in an astronaut suit, whatever you wear, the helmet, you also have this oxygen mask that's given to you, because if you don't have oxygen mask, best believe you're dead. But because there is no air, the particles that can inhale and exhale at the same time, you're going to get a mask inside the astronaut helmet, right? But overall, the air density outside is zero, so outside the stratosphere is zero. So there are 3 stratospheres. So as you reach the first stratosphere, you're gonna have air density, but not as much. The first one is easy to reach. The second one is a little difficult to reach. The third one, it'll take time. The third one is the big one. After that, yeah, I'm not going to say it's easy. Easy because you reached, hard because you can't breathe. Are people watching? Let me see if people are watching. I don't think anyone will watch. Okay. Wind gust, thrust mismatch, aerodynamic uncertainty, and atmospheric density variation. Atmospheric density variation. And the main thing, the most important are the curl E trim, which is the variable, the derivative for error versus the coefficient lift. So this is the trim correction in correlation to the error that you got, and this is the trim correction in correlation to the coefficient lift, the lift coefficient. So this is the error correction trim in correlation to the derivative. So in correlation to the derivative, this is the error correction trim, and trim in correlation to the coefficient lift. Right. Surely it's not going to be that small. So just plain like easy what is going on. It is not going to be that small. Ain't that small. 100%. I mean you have 4 sections combined in one. So easy. Calm down. What is going on? And have 2 examples. 2 examples for this section. This section that explains the maths, derivation and stuff. Where you perform the mathematical derivations and equations. Less English, more math. English must only be core explanation. So understanding the trim. So trim means equilibrium flying. Now at trim, summation of pitch moment is 0. M being the pitch moment. Thus the rotational acceleration will be 0. The pitch rate Q becomes 0. The vehicle therefore maintains steady longitudinal motion. Suppose the disturbance does appear, and because some disturbance appear, the pitch moment will always be greater than zero. Because if you look at a rocket or if you look at a missile, when there is disturbance, you're not going to go down. You're going to go, at most times, you're going to go up. Now, in some cases, maybe it may go down but the only reason it went down was not because of the wind disturbance, but because of how you operate, or maybe there could be a malfunction. There is a time when it can go down, but that going down is only because the rocket or a missile especially, it goes phew, right? It goes up and then goes straight. And when the wind, if there's more wind, there's a disturbance, it usually will have a pitch up. But either or, the pitch disturbance will be greater than zero, 100%. Even nose down, nose up, angle, change, aerodynamic uncertainty, anything. The pitch disturbance will be greater than zero. And because you know for a fact that the pitch disturbance will be greater than zero, the summation for that pitch moment will not be equivalent to zero. The adaptive guidance systems will therefore generate the restoring control moment where the pitch control moment will be less than zero, so that the disturbance for pitch moment and the control for pitch moment is equivalent to zero, and the equilibrium is restored. So for example, the pitch disturbance is 5000 nanometers. Initially summation is 5000 because obviously you have 5000, right? And obviously because if you have 5000, this can be like 5000 plus 0 plus 0. There is other uncertainties. Definitely there is other uncertainties. We're not saying there isn't, because the disturbance, again, we know that there's so many factors that plays a role, but for now we're going to say that the pitch disturbance is 5000, right? The 5000 nanometers, which means the summation of m is 5000 nanometers. But in reality, you're going to consider other stuff like the air density. You're going to measure that. The aerodynamic uncertainty, you're going to measure that. The wind gust motion, you're going to measure that. Definitely. And so because the summation of m is 5000, which is not zero, the rotational acceleration will be greater than zero, and the rocket begins to pitch upwards. So the adaptive control will compute the elevator correction. So the elevator correction will be zero, and because the elevator correction is greater than zero, which means the nose will pitch up. It's going to go upwards. The tail lift appears. The tail lift will be greater than zero, and the restoring moment will become minus 5000, meaning 5000 down, because equal and opposite, right? If we have hardest punch, you're going to receive hardest punch. So 5000 minus 5000 is 0. And so the rotational acceleration will be 0. Can we do example 3? Wait. Can we do example 3? But this time we have everything in correlation. Can we do one more example? Can we do example 3? Can we do example 3? But this time, it's reality. Like, it is a reality. Like, we have the wind gust value, the aerodynamic uncertainty value. We got the wind gust value, the aerodynamic uncertainty value. Got the, whatever uncertainty plays a role, whatever uncertainty plays a role when the rocket or when the missile is, in air. Do I really have two views? Why do I have two views, not one? Okay, because I left it open. Never mind. Wait. If you are a shadow band on X, will people still see that you are alive? So let's say I am Shadowban and I anything for a month. Yeah, but I can't because I am Shadowman. No, I can't. I can post. I can post. I can't comment. People do see my language, which is good, which is what I want. Right. So one more example. Let's add example 3 here. I mean, this is pretty obvious. Okay, the thrust misalignment. So suppose the thrust vector shifts slightly, so the disturbance moment becomes the pitch disturbance will be 2500 nanometer. Thus, the summation of m will be 2500. The rocket rotates, so you can have the pitch rate going up. What do you mean the rocket rotates? Oh yeah, it's gonna go up. Which rocket are we talking about though? Wait. We're talking about a rocket that goes in space, not a jet rocket. Yes, convert this to latex code. Label this as example 3. Okay, yeah. So during the rocket ascent, the thrust, like the fuel consumption, because the amount of fuel that is present in the rocket will decrease rapidly. Rapidly it will decrease because the fuel continuously burns. The velocity will rapidly increase, so the velocity goes up. The atmospheric density will decrease with altitude, like I said. So as it keeps going up, right? As it keeps going up and up and up and up and up, the altitude will decrease. Not the altitude, sorry, the density, the atmospheric density will decrease. The dynamic pressure continuously changes, so Q is equal to half rho v squared. Aerodynamic coefficients also vary during the ascent. So you can have the drag coefficient, you can have the lift coefficient, you can have the pitch moment coefficient. They will continuously change. And suppose during the ascent the wind shear appears, thrust oscillation appears, atmospheric uncertainty appears. And suppose the disturbance pitching moment becomes the pitching moment for disturbance is 9500 nanometer. The rocket begins deviating from the desired ascent trajectory. So we're going to have the error being the desired position. So the position, not the position actually. Yeah, it is position where the rocket has to be, like we want it to be, minus where the rocket actually is. So the adaptive guidance system will estimate the vehicle state. So this x hat of t, x of t is the desired position at that specified time step, or that time step where the rocket, the rocket position you want it to be at that time step. That is x of t. X hat of t is the estimate. Estimate is done because in a rocket they have sensors, right? And inside the sensor they're going to give like an estimation value. Okay, this is the state of the rocket. This is where the rocket is at the moment. But again, it's an estimate because it's a sensor who's doing the job, right? So obviously, even though they can go accurate, but there can be mishaps and whatever. Like it's not like it's going to be 100% perfect. The controller computes steering correction. So U of t will be Delhi. So that's a steering correction. So let's say, for example, if you want the rocket to be in this position, but the rocket is right there, so you would have to like maybe turn it to the left. I know it doesn't turn to the left, but like if you think in a car scenario, right? So if let's say, for example, you want the car to be here, but the car is right there, you would have to turn to the left to make sure that you're in the right trajectory. Same thing there. They'll do the program so that the rocket doesn't end up there. The rocket ends up somewhere in this region. It won't be exactly here, like per se, like 100%, but maybe like somewhere here or here, depending on the accuracy. But as long as it reaches within a region. Or a thrust vector correction. So what's a thrust vector correction? What is a thrust vector correction? Can you explain what a thrust vector correction is? Can you explain what a thrust vector correction is? Convert this to latex code. Actually, Samara waited it because this is inside an example. Waited it today. Actually, convert this to latex code. What he just explained. Convert it to latex code. I have my own monitor too. If you did not know, I have my own monitor. Right? This is what having a good career does to you. Get your own monitor. See, I can literally see it from here. You know what? I'm not going to see the laptop. Increase the brightness. Just to prove it to you guys that I have, alhamdulillah, I have a good career. I know people say, oh, you're Muslim. I don't give a shit. I'm honored to have a career that I have, that I'm getting a free, a free monitor, free adapter, free headset. What else can I ask for? I'm glad, I'm honored. So first of all, let's finish this. So the thrust vector correction, the U of t, so you're going to do the thrust vector correction. Restoring the aerodynamic and control moments appeared. So obviously the control for pitching moment must be less than 0, because at the moment your pitching disturbance, the pitch moment, the disturbance is greater than 0. You want to balance that, right? You want to correlate that. So if you have something less, you want to have it more. If you have something more, you have it less. And so when you add them, when you add the higher value and you have the same value but in subtraction, you get 0. So thus you're going to have the rotational acceleration being 0. This arrow does not mean equal 0. It means that it'll approach we are seeing that this is limit as the rotational acceleration reaches 0, right? And the reason we write that is because it is a continuous factor. Because it's a continuous factor, we're not going to have directly 0, meaning we're not going to have, let's say if this is, what was the value, 9,500, then we're not going to have minus 9,500 directly. So you're going to have maybe minus 1,000, minus 2,000, minus 3,000, minus 4,000, maybe 6,000. So it's like an exponential graph going down. You're going to have a very high increase, very high decrease. Then it's going to be, when it reaches minus 9,000, it's going to be like minus 9,000, minus 9,105, minus 9,110, maybe minus 9,100, maybe minus 9,200, minus 9,350. It's going to go slow and slow and slow and slow until it reaches that. But the difference between the disturbance and the control will be 0, but it's going to take time. And we want to eradicate that. There is Kalman filtering, but we are not doing Kalman filtering yet. And so thus the rotational movement will approach 0. And the pitch rate will also approach 0. The rocket will gradually return towards the nominal ascent trajectory. The adaptive rocket guidance system continues to compensate for the fuel mass variation, aerodynamic uncertainty, atmospheric density change, thrust mismatch, whatever. Long story short, whatever the disturbance we have because of these, whatever disturbance we have, the pitch control will compensate that. So the pitch control will actually do the opposite of what it has at the moment. But the opposite or the uncertainty or whatever, these happen all because of those here, right? All because of those there. During the high-speed atmospheric ascent, so you're going to have the real adaptive missiles that compensate for the wind gust, aerodynamic uncertainty, thrust mismatch, atmospheric density variation, trajectory, anything, right? Should we do a Python program? Why not? Let's do a Python program for example 3. Why not? Python program for example 3. Let's actually no way. Julian Alvarez is in PSG. What are the values that he said? I is 4500, dt is 0.01, t final is 40, n is the t final divided by dt. Time will be np dot zeros n, theta will be np dot zeros n. So n number of time steps, n number of rotational acceleration or rotations. So delta TBC np dot zeros disturbance. So initially everything is 0. And then for I in range n minus 1, mass is 550,000 because that's the mass, right? Wondering what's 50,000? Okay, stop. Can you explain the Python program again? Just one by one. Like, what is going on? Break them into sections. Explain what is going on. Obviously, NumPy and Matplotlib, right? What does 4,500 mean? So this is the rocket rotational inertia. So larger the rocket, harder to rotate. Smaller the rocket, easier to rotate. Okay, I is equal to 4,500. This refers to the rocket inertia. The simulation time, so dt is equal to, that is easy, 0.01, t is equal to 40, and will be int of t final 40, so int of t final, actually, or we can just do t final dt plus 1, right? And then we're gonna set the theta of, actually initial, we need the, let's look at the code again. We need the initial time theta, and we need the initial time theta. The time will be np dot zeros, and theta will be np, how do you write np dot zeros, and you need the times, you need the time, you need the theta. The disturbance, control, Q, and delta TVC. Not done yet. Control disturbance and theta 0. Therefore, I in range n minus 1, mass will be 50,000 minus 700 times time of I. Okay. What's that there? Slowly, just slow, calm down, slow, calm down. What is going on here? Like, don't explain in terms of code, explain in terms of maths. Don't explain in terms of code, but explain in terms of mathematics. For I in range n minus 1, so t1, t2, t3, t4, t5, all the way until tfn minus 1. M of 0 is 5,000. Oh, 5,000 being the initial fuel mass, like the fuel, like how much fuel exists in the rocket, and the every second is going to change by 700. We can write for I in range n minus 1, then m of t. No. Okay, we can keep that. And m of t will be I forgot to mention it. So m of 0 be 50, 1 to 3. 700 times t. Is that an error? All right. Yeah, as the fuel burns, yeah. So we're seeing that the mass will increase by, not increase, decrease, like the fuel rate will decrease by 700 every second, and the velocity will increase by 18 times per second from this initial velocity, which is a v naught. So v naught is 300, but you didn't mention that. That's the thing, you didn't mention that, right? You have to mention that. And velocity of t will be your velocity naught, v0 will be 300. Not 300, let's go 3000. So we don't have to mention it, but it's good practice. V of 0 plus 18 times m of t, no. The time of I. The Q dynamic is half rho v squared. If 5, this section here, atmospheric density decreasing, so rho will be 1.225 times. We have to this part only. Q dynamic would be that. Between 5 seconds and 12 seconds, a strong disturbance will appear. If the time is between 5 seconds and 12 seconds, the wind gust will be 6,000. But in reality, let me finish all those. There is something I want to change. Actually, let me copy the entire okay. Copy the entire wait, let me copy the entire first. Delete. So obviously this is your rocket inertia, like the center point. So harder the larger the rocket, harder to rotate, smaller the rocket, easier to rotate. And that's the rocket inertia. This is the infinitesimal time step value between the two time steps, between two actions. Because the actions can be a change in velocity, the actions can be change in your aerodynamic uncertainty, change can be anything, right? The final time value. The number of values, the total number of values. Why? Because we don't know how many values will be there, right? We're going to call that n, because again, this is in reality. And time, obviously, time value. Rotational angle value, pitch rate value, the thrust variation correction, so how much thrust, so how much fuel, like how much thrust slash fuel consumption needed at that time step. Pitch disturbance, pitch control control as in, so this is the, we'll just write opposite of pitch disturbance. So this is the complete opposite of pitch disturbance. Initial, why do we write np dot radians 8? Why? Initially so initially rocket is already tilted by 8 degrees. Initially the rocket is already tilted by 8 degrees. General equation for the mass, the fuel consumption, actually the total overall fuel mass inside the rocket, how much it's losing per second. So this indicates how much fuel mass is lost per second, increase in velocity of the rocket per second, atmospheric density, because again, remember I told you it will be an exponential curve. Yeah, it will be an exponential curve because when you reach the first altitude, the atmospheric density will decrease heavily. It's going to decrease because when you go all the way up, you can't breathe. It's not like you can't breathe, but the way you breathe and like how much oxygen you're going to inhale, it will be very low. Then from first to second, it is going to be a little more difference. When you look at the graph, instead of like steep, we have a graph like this, like a slanted, and then from second to third stratosphere is going to be like extremely low. Then when you go for fourth stratosphere, it's going to be vacuum. Vacuum means zero. There is not almost equivalent to zero. It is zero. The aerodynamic density. The aerodynamic density. Now here, I want to change that. You never know when it's going to be. So what they said is, if the time step is between 5 seconds and 12 seconds, then the wind gust will be 6,000. However, we can't be exactly sure that the wind gust will be 6,000 at that time step. How do I change that? I think it should be, can we instead change the, like, if the sensor is like able to detect, okay, we can't just guarantee that it's going to be 5 seconds and 12 seconds, correct? Here we can't always guarantee that it's going to be between 5 seconds and 12 seconds. We cannot always guarantee that the time step will be between 5 seconds and 12 seconds. It can be at any time. How about instead of that, why not? Because they've said time step, what can we change apart from time step? The angle. Instead, can we set that if the angle of the rocket, so like angle of the rocket is not at that state angle, is not what you desired, we can first measure the the actual angle. So we can first measure the error between the desired angle and the actual angle, and based on that, we can connect this error value to the sensor, where the sensor will then measure the wind gust based on the angle. So meaning higher the angle error, higher the gust wind. Can we do that? I think that should be the case, right? That should be the case, actually. I mean, they did actually do that. But one thing I can guarantee is it's not always going to be between 5 seconds and 12 seconds, and it's getting very slow. Yeah, so now the model will be wind gust will be 6,000. So your now model the wind gust will be in correlation to the error of the angle and K being some sensitivity constant. Okay, then what do you think I should do? Now this is for chapter 1. Do I code for the Kalman filtering part, or the rough values that I have for chapter 1? Because jumping on to Kalman filtering without any knowledge of it can be cumbersome, right? I'm going to keep the rough values, but I know that obviously you need to change that. Let's keep it simplified. Then I'm going to keep this code. I'm going to actually copy this code because I understood what's going on. I'm going to copy this code. However, I'm also going to say a warning that these are only for set values, but because we're in chapter 1, obviously, so the code will not be very accurate as compared to what you would prefer. So I am going to actually note it down. Yeah, that is fine. So during the ascent, so you're gonna have less of the fuel consumption, the fuel that exists in the rocket, more of velocity, less of aerodynamic uncertainty. And the wind gust, thrust mismatch, aerodynamic uncertainty continuously disturb the rocket. So I'm also going to say the adaptive controller compete with the steering in correlation to the thrust variation correction. So do I need less thrust? Do I need more thrust? The rocket gradually returns towards the desired ascent trajectory. So I'm just going to also mention one thing. I'm going to put a quick note here. The Python program shown above is not the actual program used, but because we have not jumped to Kalman filtering yet, the program will only presume rough values. The core reason for the Python program was not to actually model it, but understand what is going on. So the Python program shown above is not the actual program used, but because we have not jumped to Kalman filtering yet, the program will only presume rough values. The core reason for the Python program was not to actually model it, but understand what is going on. Two, 3, and 4, let's do in whole. as 1. 3 and 4, let's do like fully as 1. Section 2, 3, 4. Can you explain everything step by step? Easy. Step by step. Easy. Like, calm down. Valentina posted. Definitely Valentina posted. There's no way she will not post. Oh wow, she did not. And she did not. She definitely did not see. Knew it. sections all connected together. The flow is the lift coefficient, the correction trim for the lift coefficient, then the correction trim for the error coefficient, then the equilibrium flight. Oh wait, that's AI, right? Wait. What was the point of this? I don't understand. Did they crash? Did they crash? Wait, I'm so confused. What was the point? Oh. Did they crash? Oh, was it meant to be separated? They were meant to crash. Wait. Were they meant to crash or were they, I don't know. I don't understand what were they meant to do? Yeah, I have no clue. What was the point of that? Anyways, so three sections are connected together. So we have the coefficient of lift, like the trim correction trim coefficient. correction coefficient, and then equilibrium flight. This is the big idea. So understanding the lift coefficient, the trim correction for lift coefficient, this means how much lift is required to keep the rocket stable at a certain flight condition. Okay, so the first equation says the L trim. This means how much lift is required to keep the rocket stable. At a certain flight condition. The rocket or vehicle has weight, gravity, aerodynamic forces. If the lift is too small, then the weight will be much higher than the lift. If it's too large, lift is larger than the weight, and the vehicle will rise excessively. And so the equilibrium requires that the lift is equivalent to weight. So why do we need lift? Why lift is required? Yeah, I'm gonna say one thing, that so why lift is required? So rocket or vehicle has weight, gravity, and aerodynamic force. So if lift is too small, so if lift is too small, then LW. If lift is too big, LW, and vehicle will drop. So here the rocket drops. And here the vehicle will excessively rise.
Right.
So why does velocity matter? So the higher the velocity, the lower the lift coefficient error trim. So because it is, so why velocity matters?
And therefore, why velocity
matters? Because equation shown is higher velocity, lower trim error, the coefficient lift trim, because lift is equivalent to half rho v square SCL. So v square, so lift is directly proportional to v square. So lift directly proportional to velocity square. So if the velocity increases, then the lift will naturally increase, right? And so we do not need huge lift coefficient, because as v increases, lift will increase higher, and so we don't need that much lift coefficient. Don't need much lift coefficient, and so the lift coefficient error will decrease. The CL trim will actually decrease. Is anyone even watching? I don't think anyone will watch. Wait, I'm so confused. Did they crash?
We're through Miko.
Reach separation.
Oh my god, that's so cool.
We're through Miko.
Reach separation.
There you go. Successful hot staging separation. Followed shortly after by the other two.
Nice. Curiously, was the rocket was it meant to crash? I'm not sure. I'm not sure. Was it meant to crash or no? I mean, they crashed, right? It was meant to crash. Again, I'm not sure. Was it meant to crash? Was it not meant to crash? Yes. So understanding the trim coefficient. So we asked, how do we create the required trim lift? Control surface deflect. Whatever. The elevator moves. Suppose that the trim coefficient is greater than 0, so the elevator will move downwards. Airflow changes, tail lift changes. So the error coefficient will approach the change in lift for the tail, and the tail lift will create movement. because the tail is far from the center of gravity, the tail lift creates rotation. And so the change in the lift tail will create a pitch motion. Sorry, wait. Can you explain section 3 again? Wait, slow down. Can you explain section 3 again? Can you explain section 3 again, if you don't mind? Actually, convert this to latex code first. Convert whatever you explained into latex code. Section 2, 3, 4. Combine 2, 3, and 4. Yeah, for section 3, just explain like easy. What is going on? Section 3. Can you just explain easy, like what is going on? Section 3, explain like easy, what is going on? Explain easy, what is going on? Like, just, make the explanation easy. Make the explanation easy to understand. I'll just stop for some time.